Okay, let's continue with section B, question 8. Okay, for this question it is quite easy to do, but since I'm not plotting the graph, let's look at the readings here. Basically, you are going to get angle of incidence, and then you are going to get a corresponding angle of refraction. Okay, and the question is asking you how are you going to determine the refractive index. So again, you have to make use of some basic mathematical knowledge. So whenever you have a graph of y-axis is to x-axis, basically the gradient will tell you the difference of y over the difference of x. So in this case, if you want to get the refractive index of n, since one of the medium is air and it is going from optically less dense to optically denser, the refractive index can be given by this simple formula. So if you look at this, sine I over sine R, and if you compare with the gradient formula, which is also a ratio, you would realize that, oh okay, by turning my y-axis into sine theta I, and by turning the x-axis into sine of theta R, you would be able to get the refractive index if you manage to plot out a straight line. The gradient of this will give you the refractive index. So this would be the content knowledge you need in order to solve this question. Describe how you can find the refractive index using the set of data. So to put it in words, so since n is equals to this, n can be found from the gradient of a graph of sine theta I versus sine theta R. Okay, then for part B, obviously the glass block will be optically denser than the air, and you just need to explain in terms of the parameter that is given to you. So try not to simply state the angle of refraction is less than the angle of incidence. Okay, use the parameter that is given in the problem context, okay, so that you can relate back to the question. Then don't forget to state your final conclusion. Okay, then after that you are asked to confirm whether the refractive index is correct using critical angle. So the content knowledge that you require is that the refractive index is related to the critical angle by this, and you also need to know how the light ray will behave if how the light ray will behave at critical angle. So how will the light ray behave? First of all, you must shine the light ray. I think it's a sphere. Let me take a look. Okay, yeah, it's a sphere. So it's a semicircle. So you need to know how the light ray will behave so that you can describe it in your setup. Okay, so you can just shine it at the center point. Why is it that you must shine the light ray at the center of this semicircle? Because if you shine the light ray towards the circle, you know that it is going to be perpendicular to your tangent, and so the initial ray will not get bent. If you go and shine it like somewhere here, okay, it has a certain angle I, and your light ray will get refracted inside the glass block. So that's why it is very important that your initial ray is shined towards the center of the block. Okay, and if this angle is the critical angle, then your light ray will be along the boundary of the glass block. So you need to have this content knowledge in your mind. So now let's describe it. So first of all, we must locate this center line so that you can shine the initial ray of light towards that center line. Okay, so first of all, draw a normal such that it is the center line of the glass block. Label the intersection point between the boundary and the normal as O. Then you aim the laser at O. Is it a laser or just a ray of light? Okay, so here I don't think it's a laser. It is just a ray of light. Aim the ray of light at O such that the refracted ray is along the glass air boundary. Example, refractive angle of refraction is 90 degree. Okay, so what this step is talking about is that you have to find the angle such that your refracted ray, okay, is along the boundary, so that your theta r, which is between the normal and the ray, will become 90 degrees. So at this particular instance, the angle of incidence recorded is the critical angle, and once you have this critical angle, you can verify whether your refractive index is equals to 1 over theta c, and then you can verify whether your n is correct. So you should have another the sixth step. So, or maybe you just write down, this is to verify that the n obtained in part A is accurate. Okay, and you get a full mark. Okay, let's look at part D. Okay, so part D is another set of data from another glass block. Now, what they're asking you is that which of these sets of reading makes a better optical cable. So you need to know that in an optical cable, what you are trying to do is that, let's say you have an optical cable. What you are trying to do is that you are going to shine a beam of light into the optical cable. It is going to go through some total internal refraction, so that this is like the input pulse. It is like a signal to the computer. Okay, the input pulse is going to go through total internal refraction and then bounce, and then get out of the thing as an output. So what you want is that you want to have internal refraction. So let's analyze both sets of data and look at the refractive index. So this is the refractive index of A, this is the refractive index of B. So get it from the sets of data. And since n is actually equals to 1 over sine c, you can actually work out the critical angle for both material A and material B. Okay, so since optical fiber actually transmits signal using total internal refraction, you would want a lower critical angle so that there will be a higher, it will make the total internal refraction easier. Okay, because in order for TIR to occur, your angle of incidence must be larger than the critical angle. So by having a lower critical angle, basically your angle I do not need to be so huge. So therefore, glass block B is better. Okay, for this case it's pretty simple. Make sure you draw your ray of light and then have a normal, measure this angle and have the same angle of refraction. Do it again properly, and this angle should be the same as this angle. Then again draw the normal. It should be perpendicular to the tangent of this, and yep, it will get out. Okay, then don't forget to indicate the direction of the beam of light. Can? Okay, question 9. Question 9 is on your electricity. So to calculate the power dissipation at normal brightness, you need to look at the power rating of the lamp. So this is the normal operating condition. Substitute these two values into your P equals to VI formula, you'll be able to get the power dissipation. Okay, then after that, you are told that this circuit is set up. So if you look at this circuit, it is very similar to a typical potential divider. So they are asking you why is it that the lamp doesn't light up. So the reason is because the connection of the voltmeter. Now why is it that if you connect your voltmeter like that it won't work? It's because the voltmeter is actually having a very huge resistance. So this is almost like an open circuit. Okay, this is like as if you go and put a piece of wood in between the two wires. The circuit will not work. Just for your information, ammeter is something that is having very low resistance. The reason why is because you do not want to have an ammeter that is affecting your the circuit that you are trying to analyze or measure. That's why you want the ammeter to have very small resistance, okay, so that it won't affect the current that is flowing through. Voltmeter on the other hand is usually connected in parallel, right? So you want the voltmeter to have very high resistance so that it draw as little current from the circuit that you are measuring. So that's why they purposely make the voltmeter to have very high resistance, but the ammeter, they are making it to have very low resistance. This is for your extra information. Not extra information, I mean extra information for this question, but you should know this for the syllabus. Okay, you are supposed to know. So how to explain this? First of all, state that the voltmeter has very high resistance. Then explain how this high resistance is not allowing your lamp to be light up. So since your voltmeter is connected in series, the effective resistance of the whole circuit becomes very high because it's series. All the resistance will add up. So hence very little current can flow and therefore the lamp will not light up. So state the fact, explain how this fact is affecting the circuit, and then answer to the problem context. Okay, then after that in part 2, state the approximate reading on the voltmeter. So it should be almost 3 volt. The reason why is because, like I said, you can treat this voltmeter, since it is connected in series, to be a resistor. And because just now I have already said that the resistance of a voltmeter is very high, and since they are in series the EMF is being shared, right? And the sharing ratio depends on the resistance of the component. So if this guy is having very high resistance, it is going to receive almost all the EMF from the battery. So since if you look at the table here, the battery is having an EMF of 3 volt. Now I have to point out that even though they say that this is singular battery, right? So some of you may be wondering, oh, okay, I have 2 batteries, shouldn't this be 6 volt? Now the thing about this is that if you look at the circuit diagram, can you see this dotted line in between? This dotted line is indicating that both of them combined together will give you 3 volt. Unless the circuit diagram is drawn with a solid line, then it will be 3 plus 3. But in this case it's dotted, so we have to treat this as one whole battery that is 3 volt. Okay, so back to the question. High resistance in series. In series, EMF shared by the ratio of resistance. The higher the resistance, the higher the EMF is going to receive. So therefore, we would almost have all the EMF. So hence, we can say that it's almost 3 volt. Okay, why is it that it is not 100% 3 volt? Because you still have some bits of resistance here. So majority of the EMF is here, but a tiny bit will be across here. So therefore, you cannot say that it is equals to 3 volt. It is almost there. So explain again that the voltmeter is acting as a resistor with a very high resistance, and because it is connected in series, and so the most of the potential difference is across the voltmeter. Yeah. Okay. Then after that, you are asked to draw the correct circuit diagram. Okay, and since you are measuring the lamp, the voltmeter should hug onto the lamp. Okay, by hugging it means that it should be connected in parallel. And of course, this ammeter can be here, as long as it is on this branch. Yeah, and don't forget the switch. Okay, then after that, you are asked to show the IV characteristic. Now, in order to get this IV characteristic, you have to find the resistance. Okay, so what you need to do, express the V equals to IR and make I the subject. Now, why make I the subject? Because I is the y-axis. So you want this side to be the y-axis side, this will be your x-axis side, and you realize that the gradient that you are getting is actually 1 over R. So from the table, you will get I equals to 0.2, V equals to 3. Where do I get this? Which table? This one. The normal operating, what do you call that? Voltage and current. Oh, okay. If you look closely here, you you could even see that they actually give you the hint. The voltmeter is very high resistance, ammeter is very low. Okay, anyway, so let's use this on here, and then you can actually find out what is your resistance. So go and use the formula, put in the value, and you'll be able to get 3 divided by 0.2, 15, this is around 15 ohm. Okay, that's your resistance. So down here, actually a simple way is that you know that when V is 0, I is 0, correct? Because if you don't have potential difference, you won't have current. So you know that first point, 0, 0. Second point, you can use this reading here. So actually, you don't even need to work out any formula. You just need to know that it's 0, 0 to, do you need? Let me think. No, it is going to be a straight line. You see, this is y equals to, this is the gradient times, and this gradient is a fixed gradient, right? Because r is fixed. So therefore, you will have a straight line passing through 0, 0. So the second point is 3 volt to 0.2 ampere. So 3 volt to 0.2 ampere. From this relationship, you know that it is going to be a straight line because you just work out that r is going to have a fixed value. So the gradient is going to be constant and it's going to be positive. So ta-da! This will be your relationship. Okay, and explain the shape of the graph. So since this is a straight line graph passing through 0, 0, actually we have already assumed that this is ohmic, because once you use this, this equation is only applicable to ohmic components. So it is ohmic, and explain the shape of the graph, and the gradient, you have to say that the gradient represents 1 over r. Okay, why 1 over r? Because we just worked out, right? If you want to make I the y-axis, then the gradient is not r, it's 1 over r. Okay? Okay, let's move on to question 10 regarding electromagnetic forces. So, look at this diagram. What it has is that there's a pivot, and then there's a beam with a pointer. At this end, you are going to have a magnet. Now, what you mean by inelastic string? That means this thing is not acting like a spring. Okay, it is like a unstretchable string. Okay, so whatever movement translate, whether the movement is going up, the movement is going down, is going to translate directly to this point and hence the beam. So what happens is that if you pass a current through this solenoid will produce an electric field. Of course, you have a soft iron core to help to make the field more focused. So if there is a magnetic field being produced here, it's going to interact with the magnetic field from this permanent magnet. So there will be either an attraction or repulsion, and because of that, then there will be a force acting on this point, and because there's a pivot here, then this force would produce a turning effect on the pointer, and this turning effect, depending on the deflection, can tell you how strong your magnetic field here, and therefore how strong the current is. So basically this is an ammeter. Okay, now then in part A they are asking you to describe. So what I have said earlier on is basically what you need to write it down in part A. So before looking at my answer, you should try to write it on your own, because I have already told you about the mechanism, right? So pause the video, okay, go and write it by yourself, or check through your answer to see if you have missed out any point, okay, regarding the mechanism or regarding what I have just explained to you. So once you have tried it on your own, then check against my answer. Okay, I want you to use as much scientific terms as you can. What do I mean by scientific terms? Like moment, forces, interaction, magnetic field from either the solenoid or from the magnet. Use words like turning effects, use words like deflection. Okay, ready? Okay, so how are you going to explain? First, you start off with this part first. So say that when the current flows through the solenoid, then this solenoid is going to produce a magnetic field. Now this magnetic field is going to interact with the magnetic field from the permanent magnet. So use words like this, conjunction words. As a result, then there will be a force, and this force will act on the magnet and create a turning effect on the pointer. So you see here, turning effect. This is a special term. You need to learn this. Okay, don't say it rotates the pointer, don't say it flips the pointers go up. It is a turning effect. So therefore the pointer turns until it reaches an equilibrium position. So again, scientific term here, will it turn indefinitely? No, right? It will only turn enough so that it reaches its equilibrium position. And basically this equilibrium position will indicate the strength of the current flowing in the solenoid. Okay, I hope you have all the scientific terms stated. Okay, while you are studying, it is always good that while you are going through paper like this, structured question, you always write down what are the terms that has been used: turning effect, equilibrium position, as a result, and all that on a list of vocab. It is like learning English, but these vocab are so-called the science vocabulary. Okay, and as long as you become more and more familiar with this, you will improve on your structured question.